All right, guys, so what we're going to be looking at in this review is we're going to be going over the review for applications of derivatives. Now, there are three different ideas we're going to be talking about. We've got our optimization that we've talked about. We're also going to be talking about linearization and related rates. So let's go ahead and jump on into each of these, okay? Number one says Joe Biden has a 216 square meter rectangular plot of land that is used to harvest blah, 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 blah. You've read it all before. You just want to know how to do this problem. So when I look at it, it says it's enclosed by a fence and divided into two equal parts by another fence parallel to one of the sides. So we're doing an optimization problem here. So what I'm going to do is here is my rectangular plot of land with a fence that is dividing it between. So remember, there are steps that we use when we do optimization, okay? So I look at this, and this is like the width, this is the width, and then I've got a length here, and a length here. Well, if I look at this, I've got, again, my second step here is to make my optimized problem equation, and my constraint equation. The constraint equation in this problem is the fact that the area must be 216. So 216 must equal length times width. The optimized problem is I want to require the smallest amount of fence. So maybe we could say F is equal to, we need 2 W's and we need 3 L's. So that is what we are trying to optimize. Now what we do, remember, step number 3 is we just get the W or the L all by itself in the constraint equation. Let's say I want to get the W by itself. So W is equal to 216 divided by L. I take that and I put that into my optimized equation. So I get 2 times 216 divided by L plus 3L. When I do that, I multiply this together, and just in the interest of time, I get 432L to the negative 1 plus 3L. Now I take the derivative of that for step 4. So F is equal to that. So step 4 is going to be negative 432L to the negative 2 plus 3 is equal to 0, because that's what we do, is we set that equal to 0. Now I just move the L squared down to the bottom, and I minus the 3 over. Then I multiply the L squared over, so I get negative 432 is equal to negative 3L squared. Then I divide both sides by 3. When I do that, I get 144. So this value is 144 equals L squared, which means I now take the square root of both sides to get L is equal to plus or minus 12. Only the positive makes sense. So that's going to be the dimension, the length of my outer rectangle. I also need to know the width. So I go back to my constraint equation and I plug 12 in. So 216 divided by 12. When I put that into my calculator, I get 18. So I can see that the width is going to be 18 when I plug that back in. It also wants to know how much fence would be needed. So I have to plug my 18 in for W into my fence length and my 12 into my L to my fence length. And so I get 36 plus 36. So I have 3 different answers here. Okay, the dimensions are 12 by 18, and I'm going to need 72 meters of fencing. Now, again, I know I went through that kind of quickly, but these are optimization problems. They always follow the same steps. So that is your answer to number 1. Number 2, we've got Regina Phalange buying a mystical box to keep her puffer fish with a square base X on the side. You've read it before. And then, strangely enough, it actually gives you a cost equation, which is kind of nice because that automatically is that's telling you automatically what your optimized equation is, so we don't have to come up with one. So I'm going to optimize C equals 5 times x squared plus 4xy plus 10xy. And then we know as well in this problem that if I were to draw a picture of this, I don't need to know a ton about it, but I know that this is 1125. I've got a square base and it's y tall. So my constraint equation in this problem is going to be that the volume is equal, I want 1125 to be equal to x squared times y. So that is my constraint equation in this problem. So there's step 1 and 2. Step number 3 has us getting that y all by itself in the constraint equation. So y is equal to 1125 divided by x squared. Now what I'm going to do is plug that in everywhere that I see a y. So I get 5 times x squared plus 4 times x times 1125 over x squared plus 10 times x times 1125 over x squared. Okay, so I've got all of that. Now I'm going to try and simplify that down just a little bit before we actually take the derivative for step 4. So I can see this x and one of those x's is going to cross out, and then 4 times 1125 gives us 440. Oops, I didn't type that in right. 4 times 1125 gives us 4,500. So what I have here is 4,500 over x, and then I've got plus x squared, and then I'm going to times that 5 in there in just a second. Here I get 11250 over x, because 10 times 1125 is 11,250. Then I've got x and x squared, but one of those cancels with one of those. So what I have here is 5x squared plus, when I multiply 5 times 4,500, I get 22,500 over x plus 11,250 over x. Well, I can add those two together. When I do that, I get 33,750 over x. So this equation is 5x squared plus, I know it's weird in big numbers, 33,750 over x. So now what we need to do for step 4 is we need to take the derivative of that. Okay, so I get 10x plus, I'm going to move that the x up to the top and make it -1, so I get negative 33,750 times x to the -2, and I'm going to set that equal to 0. Just like we've done so many times before, negative 33,750 over x squared is equal to negative 10x. Then I multiply the x squared over, and just to save myself some space, I'm going to make that x to the 3rd. Then I divide by negative 10, so I get 3375 is equal to x to the 3rd. And then I take the cube root of both sides to find out what that is going to be. So in this case, the cubed root of both sides is equal to 15. So x equals 15. Well, it wants to know what values of x and y are going to minimize the cost. So now I need to find, I know what x is. I know x is 15. I need to plug 15 in to find out what my y value is. So I go 1125 divided by 15 squared. 1125 divided by 15 squared gives me 5. Okay, so I get 5. So those are the values of x and y in this problem that will minimize the cost of the tank. Okay, that is number 2. And if you've got all the friends references in this problem, congratulations. I'm very proud of you. Question number 3. Okay, Louisiana Purchase decides to open a store to sell all of the BYU fan gear that he found in his basement while cleaning so he can afford bionic knee replacements. A showroom for the store is to be rectangular with walls on 3 sides. So I've got walls on 3 sides. And on this side, I've got a 6-foot door opening on, let's see, so I've got my room here. Okay. It's only all going to be open on 3 sides. So I actually need to erase this side. I don't need that one. The door openings actually don't matter on the side because the showroom is going to have to be 800 square feet. Okay. So it wants to know, it's even though I've got door openings on the side, they actually don't matter at all. Because like there's a door opening here, 6, 6. So I've got 6 there, I've got 6 there. And then there's a 10-foot door opening on this side. Okay, so it wants to know what dimensions will minimize this space that's used. And you'll see that those numbers actually don't matter in just a second. So here is our optimize equation. So I've got optimize right here. And I've also got my constraint. My constraint is that the area has to be 800, okay? So my constraint is 800 is equal to the length times the width, because this is still the length, this is still the width of the actual thing. The optimize equation, when you think about it, that's going to be like the perimeter that we have. So that's going to be like L minus 6 for this side, plus L minus 6 for the other side, plus W minus 10. So if I were to simplify that down a little bit, I would get 2L plus W minus 26 for my perimeter there. So now what I'm going to do is get one of the letters by itself in the constraint equation. Doesn't matter which one. So I'm going to get W by itself. Then I'm going to plug that into my perimeter equation, 2L plus 800 over L minus 26. Then I'm going to take the derivative of that. Well, the derivative is 2 plus negative 800 over, or times L to the negative 2. I set that equal to 0. This should look very familiar from what we've done thus far. So I get this right here. Then I divide the negative, or I move the negative 2 down to the bottom. Multiply it over, so I get negative 800 is equal to negative 2L squared. I divide both sides by negative 2, so I get L squared is equal to 400, which means L is equal to 20. Once I find that, I need to know what are the dimensions. I take that 20 and I plug it in to my constraint equation to find out what the width is going to be. So 800 divided by 20 gives me 40. So this room is going to need to be 20 by 40. That is how big the room is going to be to have all of these things be true. Okay? Hopefully that one again kind of made sense as well. Now luckily we're to the point now where these problems do not take nearly as long. We are using linearization on both 4 and 5 to try and do an estimate of this function right here at, and it really should say at x equals 1. I mean, that's the number that's really close. So I take 1 and I plug it in for x, 1. And then to find out what y1 is, I take that same value and I plug that in. So 5 times 1 squared minus 7 times 1 plus 3. That's 5 minus 7 plus 3. That gives me positive 1. So I've got y minus 1 is equal to find the slope, what we do is we take the derivative. So I get 10x minus 7. And then I plug that in, I plug the x value in for that to find out what the slope is, because that's what tells us the slope of the tangent line. So now I've got this equation of my tangent line, and what we do is we now use that to try and estimate what the function value would be if I plugged 1.002 in. So I get 0.002 times 3 is 0.006. I've got y minus 1, so I add the 1 over to the other side, and I get 1.006 as my answer to what that linearization would be. Hopefully that one made sense. Linearization is a lot easier than what we were doing previously. Same thing here. I'm going to use linearization to estimate 2.70. So I've got y minus y1 equals m times x minus x1. And it tells us what we should use as our e value, or as our x value, we should use e. So I have x minus e, which is just a number. Then if I plug e into that equation, I get the ln of e, which is just 1. So I've got y minus 1 is equal to find my slope, what I'm going to do is take the derivative of ln of x. I get 1 over x. Then I plug e in. So I get 1 over e. That's going to look bad, and we'll talk about how to deal with that in just a second. Now I take 2.70 and I plug that in. Okay, so I have 2.70 minus e times 1 over e. And I realize these problems are supposed to be done without a calculator, but there's no way you're going to be able to figure that out. So I'm going to type it in real fast, and when we do that, we get negative 0.0067, okay, is equal to y minus 1. So I add the 1 over to the other side. When I do that, I get 0.9933, which again, I know that's not normally how linearizations work because you're supposed to be able to do it without a calculator, but we had to use it in this instance. So hopefully, again, that one makes sense on how we got that answer. Now we're to some related rates problems. So Lily goes hunting in the Amazon for a new way to get to class early and gets bit on the leg by an eastern hognose snake, which in turn gets infected because she refuses to touch the bitten area because she doesn't like snake bites. She only likes doing math problems. Assume that the area infected is circular. So I've got the area of a circle right here. If the radius of the infected area is 3 millimeters and growing at a rate of 1 millimeter per hour, what is the rate of the infected area? Now, again, we could draw a picture, but that's all that picture is going to look like, and there's your infected area right there. So a formula that describes what's going on right there with both the radius and the area is that the area is equal to pi r squared. So we come up with our formula. Then we take the derivative of that, but remember, because this is a related rates problem, we take it with respect to time. So I get all of that stuff written right there. Once we take the derivative with respect to time, then we plug in all of the things that we know to be true. At that instant, the radius is 3 millimeters, so I go 2 times pi times 3 for my radius, multiplied by the rate at which the infected area is growing, which is 1 millimeter per hour, Notice it's growing, so I use a positive number that we put in right there. Then I get dA dt is equal to that. Then I just plug that in. If I put that into my calculator, what I get for a decimal answer is 18.850. And again, don't worry about units on these problems. It would be square millimeters per hour, but don't worry about that. It's really not that big of a deal. So that would be your answer for number 6. Number 7, we've got Myron Kaysen decide to go into business selling the wind-up life-size plastic sharks to save up for semi-professional Australian crochet team. They find the average yearly cost per item producing sharks is, we've got this cost analysis right here. If the current production of sharks is x equals 10 and the production is increasing at a rate of 2 sharks per year, find the rate of change. Okay, so again, not really a picture to draw in this problem, but we can say that c is equal to this. So what we're going to have to do is take the derivative of this with respect to time. So I'm going to go dc dt is equal to, the derivative of 10 is 0. When I take the derivative of 100 over x, I'm going to make that 100 x to the negative 1. So the derivative becomes negative 100 times x to the negative 2, and then we have dx dt written after it. If I wanted to simplify that down a little bit so I could actually solve this without too many negative exponents, I'd make that x squared. Then I have dx dt right there. Now that I've taken the derivative, we just plug in what we know. So in this case, I know x equals 10, so I'm going to go negative 100 over 10 squared. And it also says production is increasing at a rate of 2 sharks per year. Okay? Well, the x value is what the production is, so dx dt is how fast that's changing, so I put 2 right there. When I put all that into my calculator, I get that dc dt is equal to negative 2. So that is our answer to this problem, how we do that one. Number 8, Josh has a spherical water tank inserted into his stomach so he can have an aquarium with him wherever he goes. Water's being pumped into the tank at a water's being pumped into the spherical tank of radius 60 millimeters at a constant rate of 10 cubic millimeters per second through a special hose and attachment to his belly button. Find the rate at which the radius of the top of the level of water in the tank changes when the tank is half full. So I've got this sphere, okay, and you'll notice that it talks about the volume of a sphere. So I've got volume of this sphere is equal to 4/3 times pi r cubed. Talks about the radius in the problem as well when the thing is half full. So I know that's the radius. We got the volume as well. So I'm going to take the derivative of that, and I get dv dt is equal to 4 pi r squared dr dt. And it tells us in this problem that the radius is 60 millimeters, so I'm going to put 60 in there. And I know that water is being pumped at a rate of 10 cubic millimeters per second. It's going in, so my dv dt is going to be 10. So what I'm looking for now is dr dt. So if I take 4 and I multiply it by pi, and then I multiply it by 60 squared, I get a really big number, 45,238.934. Then I've got dr dt on the end, and that's equal to 10. So I'm going to do 10 divided by that number that I just got. 10 divided by that gives me it's a really small number. I get dr dt is equal to 0.0002, and that's pretty much it. That's your dr dt. I just divided 10 by this big number right here, and that's what I got. Hopefully, again, that one kind of makes sense as well. Number 9, last problem. Mr. Rollins decided to finally return home and built a spacecraft as well as a camera to document the launch of the spacecraft. The camera tracks the launch of the vertically ascending spacecraft headed to planet XY224 Rollins' homeworld. The camera is located at ground level 2 miles from the launch pad, so I can kind of see what's going on here. Here's my camera right here. Here is the launch pad right here. Here is the spacecraft going up in the air. Okay, and it says, if the spacecraft is 3 miles up and traveling at 0.2 miles per second, Rollins wonders how fast is the distance between the camera and my spacecraft changing. Well, you can see here that we have a right triangle. So I've got A, B, and C. All of those sides are talked about. So my formula to relate all of those is A squared plus B squared equals C squared. So now I take the derivative of all of that. We've done this before. I get 2A dA dt plus 2B dB dt is equal to 2C dc dt. Now let's look at all of the things that are happening at that instant. The spacecraft is traveling at a rate of 0.2 miles per second, so dB dt is going to be, because that's how fast the spacecraft is moving, 0.2. We also know at that time it's 3 miles up, and this is always 2 miles right here. So what I'm looking for, I can say, because dA dt, the distance between the camera and the launch pad, is never changing, dA dt is 0. So all I really need to know, I want to know what dC dt is. In order to find that, all I really need to know left in this problem is c. To find that, we're just going to use Pythagorean theorem. So I'm going to say 3 squared plus 2 squared is equal to c squared. So 3 squared plus 2 squared, then I take the square root of that, and I get that c is equal to 3.606. So that's what that side right there is. Now I just go plugging in everything that I know. 2 times 2 times 0 plus 2 times b is 3 times dB dt is 0.2 equals 2 times c is 3.606 times dc dt. Then I just figure out what these are. So I find on the left-hand side that this is 1.2, and then 2 times 3.606 gives me 7.212 dC dt. Then I just divide by 1.2 divided by 7.212, and when I do that, I get that dC dt is equal to 0.166. That is the rate at which the distance between the camera and the spacecraft is changing. It's positive because that distance is getting bigger as the spacecraft goes up in the air. I know I went through all of those fairly quickly. Hopefully you kind of understood how to do those. If you can do these, you will be just fine for the test.